Please mute your microphone. Mute your microphone. Yeah, mute your microphone. Row number 236. So unfortunately, there is a waiting room here, so I have to keep checking the waiting room just to see if there is an alert entry. So this was a mistake. I should not have included the waiting room here. Should be automatically, all of you should be allowed to automatically join the meeting without any waiting room. So 9 people are in the waiting room. Okay, admit all. 5 in the waiting room. So I think from the next class, I will not include the waiting room. So it's going to be a nuisance to keep checking the waiting room. So I think I will share my PowerPoint. Here is my PowerPoint, but where is that? Participants, admit all. Admit all. So can any one of you turn on your microphone and let me know whether I'm audible or not? Am I audible?
Yes, sir.
Okay.
Audible.
So for clarity, I think I will turn off my video so that there will not be any lagging in my internet connection. So it's very unfortunate that inadvertently I included a waiting room here. I have to keep checking the participants entry here and keep admitting everyone. So from the next class onwards, I will be a little bit more careful. So yeah, I hope, yeah, I have to keep this thing. There are 6 people in the waiting room. This I will have to take care of it in the next class. Okay, so it's already 2 minutes past our scheduled time of what is that, 11:30. So I will begin my lecture. So this is the topic which we will be covering in this semester. I have to see that everyone has joined. There are 77 participants and 2 are in the waiting room. So I will cover unit 3 of your syllabus. That will include scalars and vectors, and also tensor analysis. I really hope everybody has joined, because if I start my lecture, I would not be able to monitor the waiting room. I have allowed the waiting room inadvertently. So yeah, 82 participants have joined. I hope all have joined, because I would like to minimize that particular pop-up where the participants and the waiting room is visible to me. So I will minimize this. I hope everybody has joined so that I can continue with what we are planning to. Or just one student has arrived again in the waiting room, 208. So this is a little bit of problem with me. So I will start with basics of scalars and vectors. Another one, Laram Sa about to. So I hope everybody has joined, because I really wish to turn off this participant monitor. This has never happened. Now Mariela Rochami has arrived and she's in the waiting room again. Okay, so I think everybody knows what the vectors are, what the scalars are. So we know that scalars are those quantities which only has a magnitude and which does not have any direction. But vectors are those quantities which have magnitude and direction. So like for example, here we have 2 vectors, vector A and vector B here. So as you see, the vector A has a certain magnitude. What is the magnitude here? The magnitude, you can measure it by the length of this. This is the magnitude of this vector. And the direction is as is given by this arrow. So one vector is pointing along this direction. And we have another vector, vector B, which also has a certain magnitude and which has the direction like this. And we know that there is a scalar and dot product, scalar or dot product, and vector or cross product. So I think everybody is already familiar with this scalar and cross product. So whenever you are taking a scalar product or a dot product between 2 vectors, then the resultant quantity will become a scalar. Scalar or dot product between 2 vectors will result in a scalar quantity. Like for example, here in this case, you take a vector A dot product or scalar product with another vector B, then the result is magnitude of the vector A multiplied with magnitude of the vector B and cosine of the angle between them, and that is the scalar quantity after taking a dot product. And here also we know that when we take a cross product between 2 vectors, a cross product is also known as a vector product because the resultant of the cross product of two vector is again another third vector, another vector. As you can see here, the cross product results in magnitude of A multiplied with magnitude of B and sine of the angle between them and unit vector n cap here, which is perpendicular to both A and B vector. So from this picture here, you see that vector A and vector B are on the plane of this screen. Then your unit vector n cap will have to be perpendicular to the screen. And the what will be the direction, whether it's coming outward from the screen or it's going perpendicularly towards the screen, that you can identify it using what is called your right hand thumb rule. Also here you know that the first vector is vector A, the second vector is vector B in the cross product between A and B. Here the first vector is vector A. That means this is, we can consider it as a rotation from vector A to vector B. So if you take like your fingers, your index and all other fingers direction as this rotation here, then the resultant vector will be, direction will be given by your thumb, right? So here in this case, if you take A cross B, your unit vector or the resultant vector will have to be perpendicularly downwards to the plane of the screen. And if you take other ways, that is B cross A here, then B being the first vector here, the rotation direction will be something like this. And if you use your right hand thumb rule, then you will find that your resultant vector, your n cap, will be perpendicular to the screen and but facing towards you. It will be facing towards you, right? So that is the dot and cross product we already know. And everybody, I hope. Oh yeah, there are 3 people in the waiting room. This is such a irritating and such a nuisance. Yeah. Okay, I hope I have admitted all. So if you consider this Cartesian coordinate system like x, y, z coordinate system, and we are already familiar with unit vectors. I cap is the unit vector along the x-axis, j cap is unit vector along the y-axis, and similarly k cap is unit vector along the z-axis. So what do you mean by unit vector actually? Unit vectors are those vectors having magnitude of 1 unit magnitude, right? So it only has a direction, it represents the direction of this coordinate axis, and but it only has a magnitude of 1, like shown here. When you take the magnitude, so when you put the double bar like this is called the magnitude of the vector. The magnitude of the vector is 1. And please roll number 013 and 236, sorry, 263. I request everyone to turn off your microphone. Turn off your microphone, because that is really a problem for the rest of your classmates. If you turn off your, if you mute yourself, that would help a lot. Okay, so here you see that if these unit vectors, if they represent the direction of the coordinate axis, we know that this rectangular Cartesian system, the angle between all these coordinate axes are 90 degrees. They are all mutually perpendicular to each other. Therefore, when you take a dot product between I and j here, you see that I and j dot product is magnitude of unit vector I, magnitude of unit vector j, and the cosine of the angle between them. So cosine of the angle between them is 90, and we know that cos 90 is 0. So therefore I dot j is 0, and similarly you will see that I dot k is 0 and k dot j is also 0. But when you take a dot product of the vector, unit vector with the unit vector itself, then you see that the magnitude of unit vector is I is 1. The magnitude of unit vector is I is 1, and the cosine of the angle between them will be 0. Cos 0 is 1. So therefore, I dot I will be 1, and similarly you will see that I dot j is 1, k dot k is 1. So again, this is just a revision of what you already know. Now, what is a cross product here? So from the definition of the cross product, like I have shown you before, you see that I cross product with j will result in magnitude of I, magnitude of j, and sine of the angle between them. So as I said, in the Cartesian rectangular system, all the coordinate axes are mutually perpendicular. So the vector direction of I and j will be at 90°. And like I explained before, here you are taking a cross product between I and j. If you look at this, I is the first vector here, j is the second vector, j is the second vector, then you can consider it as a rotation like this, right? So if you take out, like if you consider your right hand thumb rule here, the index fingers and all, they will represent the direction of this rotation, and the thumb will give you the resultant vector direction, right? So I cross j will result in unit vector pointing upwards. So unit vector pointing upwards here, I cross j will be, and cap will be your k cap. Just a minute. Oh, hello. Phil, class ka lock lo duka. Class ka lock lo. So n kept your unit vector, the one we talk about here, over here, it will be along the k cap direction. So n cap will be same as your k cap, right? So here you see that you, instead of n cap, we simply write k cap here, and sine 90, of course, you know it is 1, right? Now when you take a cross product between I and k, I cross k, so I cross k, I is the first vector here, k is the second vector here, I cross k will be, you can consider a rotation like this. Now if you take the direction again using your right hand thumb rule here, you will find that your unit vector n cap will be pointing towards this direction. So what is this direction? This direction will be opposite to the direction of j cap. So n cap is simply here minus of j cap here, right? So we know that. Now here sine 90, again it is 1, so therefore this is minus of j cap. And similarly, I think we all know that j cross k is I cross I is 0, because sine of the angle between them will be 0 here, so it is 0. And I think everybody knows that this is certain basic ideas of these vectors here. Now let us talk about a scalar function. So a scalar function, we know that scalar quantities, like we know that temperature is a scalar quantity, right? So temperature, it only has a magnitude, whether it's 30 degrees Celsius or 35 degrees Celsius or 20 degrees Celsius, or a freezing temperature of 0 degrees Celsius. We know that it has a certain magnitude, but this quantity does not have any specific direction, right? So let's say, for an example, suppose you are in a certain classroom. In one particular classroom, if somebody near to you is having a fever or something, then around that person, a lot of heat will be generated, and probably, the heat generated around a body will result in a little bit higher temperature near that. If you move away from that, the temperature will change, isn't it? So in a particular space, as we consider like a classroom, temperature will be depending on your space variables, whether you are moving along the x-axis or moving along the y-axis, or whether you are climbing up along the z-axis. Temperature will be dependent on your space variables x, y, and z. So those physical quantities, or scalar quantity, which has dependency on, which depends on space variables, are called scalar function, right? They are scalar functions. Now let us quickly look at the concept of derivative. Yeah, I hope everybody has entered. Oh, there are 3 people still in the waiting room. Oh, 5 people. So in the next class, I should not include this waiting room. So like 5 of your classmates are still waiting for me to allow them in the class. So roll number 263, again you are unmuting yourself. Please mute yourself. 2001 BS263. So again, let me announce now that most of you have entered. Please open the chat box and there you type your roll number in full. Roll number in full, okay? Like 2001 BS and whatever. Yeah, another one is now in the waiting room. Okay, I think I can continue because I only have 30 minutes. So what is a derivative? So a derivative is actually a measure of how quickly a function changes with a space variable on which the function depends. Like, for example, the graph I plot here, let me enlarge it a little bit here. So let's say we have a function f, which is depending on x variables. So here is x exists. So out here, you know that this is the origin. At this origin, x value is 0. As you move along the right direction, the right hand side here, you will find that x value is increasing from 0 to 1, 2, and 3, 4, 5, like that. Now, if you say that f is a certain function which is depending on x, that means f is actually changing with x. F is a function depending on x means as the x variable changes, f value will vary according to x independent variable, right? So for example, if it goes on like this, for example, here, if you consider this point here, around this point, if you take around this point, if you take small increment along this direction, this is called, you can take it as a del x. Now, corresponding to small increment along the x-axis of this del x, now what is the corresponding change in f? The corresponding change in f will be this much, that we call it del f. And we know that derivative by definition, it is given like this, del f upon del x at the limit of del x tending to 0. This is called the derivative. Now, when del f is quite large for a small change in del x, that means your derivative will be large. Your derivative will be large. That is, the slope of the function will be large. So here you see that the slope is, when you take it like this, when you take it like this, let me draw it here. So that is called the slope. So when the slope of the function is large, then the derivative is large. So derivative is actually the slope of a particular function, or how quickly that function varies with the variable on which the function depends. Now over here in this region, you see that let's say we consider this point, and let's say around this point, let us consider a small increment in x called del x. Now here, what is the corresponding change in f? The corresponding change in function f here, as you see from this graph, it is very, very small. So here del f upon del x is quite small. Then if you take consider this derivative, that is limit del x tending to 0, then you will find that the function changes very slowly around this point. So the derivative is very quite low over there. So as I was just illustrating here, derivative is just a measure of how quickly the function changes with the variable. Yeah. Now let me move on to what is called the Dell operator. I think you already know a Dell operator in your class 2 standard also. So this Dell operator, the one I wrote here, this is not representing any physical quantity. It does not have any physical meaning at all. So this is just an operator. Operator means it can operate on scalar and vector function. It can operate on scalar and vector function, or a scalar quantity or a vector quantity, right? So if you are asking me what is the physical meaning of this del operator, yeah, the answer would be this del operator does not have any physical meaning by itself. This is just an operator, mathematical operator, which can operate on certain physical quantities like vector quantities and scalar quantities. Like, for example, the scalar function and a vector function written here, right? So, gradient. Gradient is when a del operator operates on a scalar function, that vector operation is called gradient, right? So when you have this del operator operating on a scalar function, this vector operation is called gradient of a scalar function. So whenever you have an operator operating on a certain function, you should always write the operator, the del operator, on the left side of the function, whether it's a vector function or a scalar function, right? So as you can see here, when this del operator operates on phi, the scalar function here, the phi will be differentiated with x, and phi will be differentiated with y, phi will be differentiated with z, and I, j cap, and k cap are the unit vectors along the Cartesian axis. And here we use what is called a partial derivative. So del operator consists of partial derivative with respect to x, partial derivative with respect to y and z. So the difference between partial derivative and normal derivative, I think you would already know. Yeah, again, another student, whether I would allow him or not. Okay, for this time, for this class only, I will allow all the students to join the lecture before the end of the session. But from the next session onwards, I would not permit anyone to join after 10 minutes. So here, yeah, what I was saying, partial derivative and normal derivative. So here, phi is a certain scalar function. Phi is a certain scalar function which depends on more than one variable, that is all the space variables, three-dimensional space variables like x, y, and z. So like the example I've given as a temperature. So temperature as a scalar quantity, scalar function, if you move along the x-axis in your classroom, along the x-axis, the temperature may also vary along the x-axis, and the temperature can also vary along the y-axis. The temperature can also vary along the z-axis. So that means you can have a change of the scalar function along all the three axes. Now, if that is the case, then the derivative, which is a measure of how quickly that function change with respect to the variable. So del phi upon del x, it measures how quickly that function change with respect to x. But since phi is also depending on y and z, it is not a complete or normal derivative. Whenever you have a function having dependency on more than one variables, the derivative with respect to one of the variable is the partial derivative here. So this del phi and del upon del x and d phi upon dx, they are not equal. Okay, they are not equal. So do not confuse with that. And here is what is called, someone is I think sharing his audio. Please mute yourself, whoever it is. So here is another del operator operating on a vector quantity, a vector function. Here del operator is written on the left side of this vector, and when you put a dot product here, del operator dot product with the vector a is what is known as the divergence of the vector a. Okay, I will talk about the physical meaning and all. So when you take a dot product between these two, you see that I dot I will be 1, I dot j will be 0, I dot k will be 0. So therefore the result of this dot product will be del a1 upon del x plus del a2 upon del y plus del a3 upon del z. So here you see that again, when you take a dot product between the Dell operator and the vector a, it results in a scalar quantity. It results in a scalar quantity. So that means, as I said from the beginning of this lecture, this dot operation is a scalar operation. Okay, a scalar product. So it results in what a scalar quantity. Now. Muted, unmute. Okay, now let us talk about this gradient. I hope I can try to complete this gradient in about 5 minutes. So as I said, phi is a scalar function which depends on x, y, and z. So when you consider a change in the function here, change in the function is called d phi here. D phi here is simply what it represents. D phi, what it represents is a small change, infinitesimally small change in the function. When you write d phi, d small letter d phi here, what it means is that it represents an infinitesimally small change in the function phi. Okay, so when you take infinitesimally small change in the function phi, from the law of partial derivatives, we know that like phi can also change with respect to x, phi can also change with respect to y, and phi can also change with respect to z. Therefore, infinitesimally small change in the function phi has to be written like this. D phi is del phi upon del x into dx. So del phi upon del x into dx will represent how quickly the function change. Del phi upon del x represents how quickly the function phi changes with respect to x, and dx is small change, infinitesimally small change in the infinitesimally small change along the coordinate x-axis. Again, del phi upon del y represents how quickly this function phi can vary with respect to y, and when you multiply with dy, dy is infinitesimally small change along the y. So when you consider infinitesimally small change along the y, this del phi upon del y into dy will give you the amount of change in the function phi. And also here, del phi upon del z will represent how fast phi function will change with respect to z. And when you multiply with dz, that is a small increment or a small infinitesimally small change along the z, then del phi upon del z into dz will give you the amount of change in the function phi along the z-axis when you vary the z variable, right? So this is what it means. D phi is equal to del phi upon del x into dx plus del phi upon del y into dy plus del phi into del z, del phi upon del z into dz. Okay, now next is that when we already know that there's a dot product, I think everybody knows the principle behind this dot product here. Like for example, if you take a dot product between a1 I cap plus b a2 j cap plus a3 k cap, dot product with b1 I cap plus b2 j cap plus b3 k cap. Here you see that a1 I dot I will be 1, so a1 b1 plus a2 b2 plus a3 b3. Here you see that when you write a1 b1 plus a2 b2 plus a3 b3 plus, this is equivalent to writing vector a dot product with vector b. So following that, you can write this quantity as the dot product between this quantity and this quantity. Here we already defined what is called the gradient of a function phi. So del phi upon del x I cap, del phi upon del y j cap, del phi upon del z k cap. This is your gradient of phi. And dxi cap plus dyj cap plus dzk cap. This is a small increment in the space variable, that is the position coordinate dr. Small change in the position coordinate. R vector is called the position coordinate, the position vector. R vector, which is xi cap plus yj cap plus zk cap. This is called the position vector. So small change in the position vector dr vector is dxi plus dyj plus dzk. Therefore, you can write d phi is equal to grad phi dot dr. Right. Now, here, as you can see here, this is d phi is simply infinitesimally small change in phi is simply dot product between two vectors. One of the vector is grad phi, another vector is dr vector. Okay. Now, if you look at this picture here, so let me redraw it. It's not very clear. So this is a dr vector, for example, and this is a grad phi vector. So grad phi is one vector, dr vector is another vector, and when you're going to take a dot product between these two vectors, you have to consider the angle between these two vectors, grad phi vector and dr vector. Now, if you do that, grad phi dot dr vector will be magnitude of grad phi, magnitude of dr vector, and cosine of the angle between them, cos theta. Now, therefore, your d phi, infinitesimally small change in the function phi, will be equal to magnitude of grad phi, magnitude of dr vector, and cos theta. Theta is the angle between the two vectors. Now, here we know that cos theta, this function, cosine trigonometric function, yeah, I think someone is unnecessarily turning on his video and moving around. Please stop doing that. So when you consider this trigonometric function cos theta, we know that cos theta has a maximum value. Cos theta maximum value is 1, isn't it? Cos theta and sine theta, these trigonometric functions, tan theta as well, and other trigonometric functions also, cot and cosec and sec theta and all, the maximum value are 1. We know that this cos theta will have a maximum value of 1 when theta value is 0. That means your d phi, infinitesimally small change in the function phi, will be maximum. Infinitesimally small change in the function phi will be maximum when your theta value is 0 for a fixed value of this dr vector. For a fixed value of this dr vector magnitude, you can see that infinitesimally small change in the function phi will be maximum when theta is 0. So what is the condition when theta is 0? The condition when theta is 0 means your dr vector and your grad phi vector, they are along the same direction. That means when you consider change in position vector, that is your dr vector, along the direction of your grad phi, then the function phi will have a maximum change. The function phi will undergo maximum change when you consider changing your position vector along the direction of your grad phi. So therefore, you can see that grad phi will represent or will define the direction of maximum change in the scalar function. Okay, so when you consider any scalar function, like as I discussed, the temperature and all, the grad phi or the grad of that temperature function, scalar function, will represent the direction of maximum change in the scalar function. Right. So here the theta is 0 means cosine function is maximum. That is possible only when you align your dr vector along the direction of your grad phi. Okay, so I think I will conclude my lecture here. We have already spent 6 minutes more than the more than the scheduled duration. So if everybody, I hope everyone has typed your attendance there. After you type your attendance, you can exit the meeting. Everyone must type your roll number there in the chat box, because I will simply copy everything from the chat box. So please enter your attendance. But once you enter your attendance, please do not repeat it. No need to type more than once. Even if you leave the meeting uh, in the middle, or and join again, also everything will be recorded. Whatever was there in the chat box, whatever you type in the chat box, everything will be recorded. So I will end the meeting and exit the meeting if everyone has typed your attendance.